Hey guys, welcome to question 14. So starting with part A, we have the two non-parallel vectors u and v satisfy lambda u plus mu v equals 0 for some real numbers lambda and mu. Show that lambda equals mu equals 0. So let's say if lambda and mu were not equal to 0, then we could say lambda u equals negative mu v, and therefore u equals negative mu over lambda v. Therefore u and v are parallel, which is obviously a contradiction because they are non-parallel. Therefore contradiction. So lambda equals mu equals 0. And that will be it for part I. So next for part II, the two non-parallel vectors u and v satisfy all that for some real numbers lambda 1, lambda 2, mu 1, and mu 2. So using part I or otherwise, show that lambda 1 equals lambda 2 and mu 1 equals mu 2. So we know that for these equations, we have that, well, if we have this equation, first we can rewrite it as, bring them all to one side. So lambda 1 minus lambda 2 u plus mu 1 minus mu 2 v equals 0. So since that we know that these vectors are not parallel, therefore they have to be linearly independent, which basically just means that if we want to combine any combination of them, then all the coefficients must be equal to 0 if the entire thing is equal to 0. Therefore lambda 1 equals, maybe first just do lambda 1 minus lambda 2 equals 0, and mu 1 minus mu 2 is also equal to 0. And therefore lambda 1 equals lambda 2 and mu 1 equals mu 2. And that will be it for part II. So next for part III, we have a bit of a diagram here. So the diagram below shows the tetrahedron with vertices A, B, S, C, and S. Point K is defined by that, as shown in the diagram, and the point L is the point of intersection of the straight lines SK and BC. So using part II or otherwise, determine the position of L by showing that BL is equal to 4 over 7 BC. So we have our diagram here. So a way we can do these is by using a sort of combination of, vectors to find out BL in terms of BC. So first off, we can write BC as a sort of combination of, BC can be written as SC minus SB. Let's hope you guys know your vector. And we can basically just rewrite BL as a sort of, scaled version of BC. So we know it's something times BC. So we want to prove it's 4 over 7. So that's why we put a scalar in front. So lambda. And we just sub in what we wrote before. So we can rewrite BL as lambda times SC minus SB. So the reason we do this is we can also use some scalar using SK. So BL can also be written as some combination of, well, SL minus S, yep, SB, I believe, yep, SL minus SB. So SL itself can also be written as a multiple of the vector SK. So you guys can see that, since we know it's just kind of SK extended down to BC. And what's SK? Well, we already have it. So SK is 1/4 SB plus 1/3 SC. Hopefully you guys can see what I'm going with here. Finally, we can rewrite BL as, sub that in, so mu times 1/4 SB plus 1/3 SC minus SB. And now we have two equations left of BL. So we have BL equals lambda times, we use this sort of line, so SC minus SB, and we also have these lines for BL. So equating them together, we have lambda times SC minus SB. So that was from here, SC minus SB is equal to mu times 1/4 SB plus 1/3 SC minus SB. Bit of a chunky one. Now we expand them. So lambda times SC minus lambda SB is equal to mu over 4 minus 1 SB plus mu over 3 SC. And remember our part 2, we had, if these two vectors are equal, then lambda 1, basically just the coefficients of any combination of two vectors are equivalent. So the coefficients of SC, so lambda equals mu over 3, and we also have these, negative lambda equals mu over 4 minus 1. So finally rewriting everything, we can rewrite using the first one, mu equals 3 times lambda, sub that into the second equation, so negative lambda equals 3 lambda over 4 minus 1, so that will be negative 7 lambda over 4 equals negative 1, and therefore lambda equals 4 over 7. And as you guys can see here, and from here as well, we had BL equals lambda times BC. Since lambda equals 4 over 7, therefore BL is equal to 4 over 7 times BC. That will be it for part III. Next, for part IV, we have the point P is defined by AP is equal to negative 6AB minus 8AC. So does P line on the line AL justify your answer? So this is a bit of a sort of tricky one, but what we need to do is just kind of break things up as we can. So for part IV, we can first rewrite AL as the sort of combination of equations AB plus BL. So you guys can see AB plus BL gives us AL. So we already have BL as a sort of rewriting as BC. So can rewrite AL as AB plus 4 over 7 BC. And well, let's try to break down BC in terms of AB and AC. That's just equal to AB plus 4 over 7. So BC is AC minus AB. And now we're just solving the fraction for this. That's AB plus 4 over 7 AC minus 4 over 7 AB, which is equal to 3 over 7 AB plus 4 over 7 AC. And remember, this entire thing was equal to, let's see, AL. So timesing everything by 7, we have 7 AL equal to 3 AB plus 4 AC. And the cool thing is we know that AP is defined by negative 6 AB minus 8 AC. So if you just take out a negative 2, that's just negative 2 times 3 AB plus 4 AC. So in other words, 7 AL is equal to negative half AP. And therefore, they are parallel. But they also share a common point, which is A. So since they're parallel and both pass through A, therefore P lies on the line AL. And that will be it for part IV and question A overall. For part B, we have let Jn equals the integral from 0 to 1 x to the n e to the negative x dx, where n is a non-negative integer. So n is greater or equal to 0. So starting off with part I, we have show that J0 is equal to 1 minus 1 over e. So pretty straightforward. We first sub in our n equals 0 into the equation. So the 1. X to the 0 is just 1, so 1 times something is just itself, dx. So nice and simple integration. So e to the negative x becomes negative e to the negative x from 1 to 0, which is just negative e to the negative 1 minus 1. Well, minus negative 1 actually, sorry about that, which is just 1 minus 1 over e. And therefore, that is pretty straightforward, it for part I. So next for part II, we have show that Jn is less than or equal to 1 over n plus 1. So the 1 over n plus 1 should hopefully give you a little bit of a think about integrals. So when we look at our integral, don't have to do anything insane. We have Jn is equal to the integral from 0 to 1 x to the n times e to the negative x dx. Now, the thing you guys should remember is that for, well, let's see, for e to the negative x, that the graph's going to look something like that. It doesn't go through negatives, sorry. Something along the lines of that. E to the 0 is 1, and e to the 1 is 1 over e. So between 0 and 1, e to the negative x is less than or equal to 1. So hence, when you times it through, that means overall that the integral from 0 to 1 x to the n e to the negative x dx is also less than or equal to the integral from 0 to 1 of just x to the n by itself, since e to the negative x is just some number 1 or less. And, well, the right integral is much easier to look at. So the integral from 0 to 1 x to the n dx, that's just equal to integral of x to the n plus 1 over n plus 1, 1, 0, which is just equal to 1 over n plus 1 minus 0, which is 1 over n plus 1. And hence, therefore, j to the n is less than or equal to 1 over n plus 1. And that will be it for part II. So next for part III, we have show that Jn equals n times j n minus 1 minus 1 over e for n greater or equal to 1. So now we're at the point where you guys should hopefully remember how to do your integration by parts. So for part I, we have integral from 0 to 1 of x to the n e to the negative x dx. So what we're going to do is we're going to integrate x to e to the negative x, and we're going to differentiate n minus just x to the n. So hope you guys don't lose track. What we're going to do here is integrate e to the negative x. That becomes x to the n times negative e to the negative x from 1 to 0 minus the integral 0 to 1. So if we differentiate, let's see, x to the n, that becomes n x to the n minus 1 times negative e to the negative x dx. So we're going to equate that. So the first part, so x to the n minus e to the negative 1, that's just negative e to the negative 1, and x equals 0 is just plus 0. And finally, negatives here will cancel out. So plus n times, well, x to the n minus 1 times e to the negative x is just j n minus 1. And finally, that's just n times j n minus 1 minus 1 over e. And overall, remember this was all equal to j to the n, jn. So therefore, jn is equal to n times jn minus 1 minus 1 over e for n greater or equal to 1. And that will be it for part III. So for part IV, we have using parts I and III, show by mathematical induction or otherwise that for all n greater or equal to 0, jn equals that huge thing. So starting with induction, we have the basis step, which is just for n equals 0. But we already know that for j0, let's see, 0 factorial minus 0 factorial over e to the 0, let's see. So from 0 to 0, that's just going to be equal to factorial times 1. So that in sum is a little bit of a tricky one, but just get it through. 0 factorial, if you guys remember the identity, it's just equal to 1. So hopefully you guys don't forget that. 1 minus 1 over e. And we already proved from part I, therefore true for n equals, oh, not 1, n equals 0. Makes life easy. So next, we use the assume true for n equals k. K is integer. So we have jk equals k factorial minus k factorial over e integral, not integral, sum from r equals 0 to k, 1 over r factorial. And now we want to prove true for n equals k plus 1. So from, well, first let's rewrite it. So we're going to write i.e. j k plus 1 is equal to k plus 1 factorial minus k plus 1 factorial over e from the sum r equals 0 to k plus 1 of 1 over r factorial. So from part III, we have that j k plus 1 equals k plus 1 factorial minus, let's see, oh, oops, that isn't factorial. K plus 1 times jk minus 1 over e. So using this, we can basically find out that jk plus 1 equals k plus 1. So jk, we just use the assumption here, sub that into the assumption. So that's just k factorial minus k factorial over e of the sum r equals 0 to k over r, that, and that all minus 1 over e. So now we sub it all in. So hope you guys can see. So k plus 1 times k factorial is just going to be k plus 1 whole factorial. And when we also do that, we have k plus 1 times k factorial over e, which is just minus k plus 1 factorial over e of the sum from r equals 0 to k 1 over r factorial minus, and when you look at e, you also want to try to, let's say we make it nicer to kind of sub in by having a k plus 1 factorial on top and bottom. So k plus 1 factorial, k plus 1 factorial, e. Now the reason we did that is so, well, we can just put it back into this sum over here. So when you do that, we just have, that's all equals to k plus 1 factorial minus k plus 1 factorial over e. And if you sub in k plus 1 into the equation there, well, that's just going to be, well, yeah, just a k plus 1 version of the sum. So that is just k plus 1 r equals 0, 1 over r factorial. So using that, well, that is what we wanted to prove. So therefore, true for n equals k plus 1. Therefore, statement true by mathematical induction. And that will be it for part IV. Next, for part V, we have using parts II and part IV, prove that E equals the limit of n approaches infinity of sum of r equals 0 to n of 1 over r factorial. Factorial. So looking at part II and IV, we have that Jn is less than or equal to 1 over n plus 1 factorial, and we also have Jn equals that. So, well, if you use the sort of idea there, we have the fact that part V, 0 is less than or equal to Jn, which is less than or equal to 1 over n plus 1. So if, in other words, we times everything by 1 over n factorial, everything, that's just 0 less than or equal to Jn over n factorial, which is less than or equal to 1 over n plus 1 factorial. Now, if we use part IV, we have 0 is less than or equal to Jn over n factorial, which, if you just look here, if we divide everything by n factorial, that's just 1 minus 1 over e times the sum of r equals 0 to n 1 over r factorial, which again is just less than or equal to 1 over n plus 1 factorial. So getting a bit closer here, so since we know that 1 over n plus 1 factorial approaches 0 as n approaches infinity, since 1 over infinity will eventually approach 0, we therefore have that 0 is less than or equal to 1 minus 1 over e, limit of n approaches infinity, 1 over r factorial, which is less than or equal to, well, the limit of n approaches infinity of 1 over n plus 1 factorial was just 0. So therefore, when we have the limit on both sides is equal to 0, that's just by squeeze theorem, yeah? So by using squeeze theorem, 1 minus 1 over e limit n approaches infinity of 1 over, I nearly forgot the sum on both of them, sorry. Sum r equals 0 to n, r equals 0 to n of 1 over r factorial. It's just equal to 0, since both sides, the limit goes to 0. And from there, it's just rearrangement, so 1 over e, lim n approaches infinity, n, r equals 0, 1 over r factorial, that's equal to 1. And therefore, the limit of n approaches infinity of this entire sum over here, 1 over factorial, is equal to e. And therefore, that will be it for part V and question 14 overall.